All right. Thank you. All right, so my title is 3 parts. So there is flatness, there is smoothness, and there is the Analyst traveling Salesman Theorem, which I will always write as AT-AST for like timing reason. So let's just like, a lot of mathematics is concerned with like dealing with flatness and smoothness and connection between the two. So let me just tell you what I mean by flatness, what I mean by smoothness. So by smoothness, I mean things like maybe Helder maps. So that would be C alpha, or maybe Lipschitz, C1, or maybe C1 alpha, which is just continuously differentiable maps with alpha Helder derivative. So I assume that alpha Helder continuous, it's right for everybody. And for flatness, I mean mostly 2 concepts, which I'm gonna try to explain to you. So this has beta numbers, which are not Betti numbers, what last talk was all about. So it's beta numbers, and something called Reifenberg flatness. So we'll get into that later. All right, and the Analyst traveling Salesman Theorem is something proved by Peter Jones in 1990, and I would like to explain to you. This also happens to be my favorite theorem, so I'm very happy to be here explaining that to you. All right, so the question they were trying to answer is, if you're a computer scientist, you're very familiar with the traveling salesman problem. So you have a certain number of cities, and you want to visit them, and you want to find that in some optimal time. If you're an analyst, optimal doesn't really mean much, and maybe you don't want to deal with finite cities. So the question is, given a bunch of points, and I'm calling them a bunch because I don't want to tell you how many they are. Are they finite, infinite, uncountably many, a continuum? That's all right. Given a bunch of points, let's say in the plane, when can I travel them all? Infinite time. And in fact, I don't only want the time to be finite, I kind of want it to be optimal. And I'm going to use quotation mark because it's the analyst optimal. So I don't want to upset anybody. OK, so to answer this question to you, I need to introduce these beta numbers. So I'm going to start with a picture, and then I'll write a formula. So everybody should be happy at the end. All right, so say that you have a set E. Right, so this is your set E in the plane. And so now I do multiscale analysis. So you want to look only at a certain place and location. Now, because like the harmonic analyst that lives in me likes cubes, so I will take a cube. But if you're a geometer, you probably prefer to take a ball. That's totally fine. Just imagine this to be a ball. Okay, so now I have a certain set Q, and I'm only looking at my set E inside Q. So I forget about everything. I zoomed in. I'm focused here. All right, now I want to find the best, so I want to measure how, I'm talking about flatness, right? So I want to measure how much Q is not a line. So I'm going to try to find the best fitting line. So in this case, I think like this is not too bad, right? And now I want to measure how much E is not a line. So I'm going to take the strip, the smallest strip around L, and I'm going to look at its width, OK? Interrupt me anytime you want. All right, so the idea is like, all right, cool, this is beta. But this is a kind of a little bad idea, because I told you I want to do multiscale stuff. So I better be working with some scale invariant quantity, and the width of this strip depends on how big my Q. So I need to divide by the diameter of Q. I know this is multiplied because I divided the definition. Let me write the formula, all right? So I'm taking the distance between a point from a line, and I'm taking a strip, and these points are inside E intersect Q. And now I told you I want the best line, so best line. But this has the unit of length. I want like a dimensionless quantity and a scale invariant one, so I'm going to divide by the diameter of Q. OK, and I define this to be beta infinity E of Q, where the infinity is in a posteriori naming and refers to the fact that I put a supremum here. So if you want, you can do an LP version of this, which we will not discuss. All right, and of course, let me just say that we define beta infinity E of Q to be 0 if my cube doesn't meet E. All right? So I only care about Q that actually C in my set. All right, so now we have all the tools that we need to state the analyst traveling Salesman theorem. So the theorem says, all right, this is the theorem. So the theorem is due by Peter Jones in 1990. He proved in R2, but because R2 is actually the complex plane, so he used complex techniques. And then Kate Okikyalu generalized it to one-dimensional objects in Rn. So, and this is a 92, I think. Rn, and the key word, and if you know what that means, you will be excited. If you don't know, it's not going to say anything, is the 1/3 trick. All right, so what does the theorem says? Given a bunch of points, so given E in Rn, I'm asking when does it exist a certain curve. So when does it exist? There exists gamma. So gamma is a curve of finite length. And what do I mean by this? You can actually choose your favorite meaning of that. I'm going to think about the Lipschitz image of 0, 1. Okay? Which is also, it's elementary yet not trivial to prove that rectifiable curve, finite length curve, Lipschitz image of closed intervals are all the same concept. And I want to travel through all my infinitely many cities, right? So I want my gamma to contain it. So this gamma exists if and only if a certain quantity is finite. What is this quantity? Well, I want my set to be bounded for like kind of obvious reasons. And then I'm going to look at this quantity. So the sum of beta infinity E, we know these guys. Then I take 3q, but don't worry about that. Squared infinite. And where am I summing? I'm summing over all the dyadic cubes. So the dyadic cubes are cubes with side length 1 over 2 to the k for k integer. And I'm summing over all of them. So for each fixed k, each of them is a tiling of the plane or of the space, okay? So they're all of them, but this is why I have this helping me, and this also the square. And I think, of course, I'm giving a 10 or 15 minutes talk, and so I will not have time to tell you anything about this. The only thing that I really wanted to know, if you don't remember anything about this, the one thing I want to remember is this theorem, and this is just Pythagoras. This is just Pythagorean theorem. Like the proof boils down to the fact that you get a square in there. Okay, very good. So I want to talk about what I would like to do in the future, but in order to do that, I need to introduce a couple more concepts. So I will do that very quickly. And so this theorem is a characterization of subset of Lipschitz curves, right, or rectifiable curves. And it's very important. This theorem only holds in dimension 1. And that's because topology is trivial in dimension 1. Things get way more complicated if you go up in dimension. All right, so but let's talk about something else, right? So I told you that flatness, there was this flatness, we got it, and then there is this Reifenberg flatness. So Reifenberg was a mathematician that worked in geometric measure theory in the 60s. He, in fact, passed away, I think, in 1964, climbing the Alps. And he proved something. He proved in 1960, he gave the first solution for a plateau problem, so some minimal surface stuff, without any topological assumption. And in doing so, he proved this fact. So this is Reifenberg in the 60s. So he proved that looks at that epsilon d flat set can be is such that okay, I can do that. Okay. So if you have an epsilon flat set E, which I did not define, I will do that. I promise. That's not true. I will not do that, but it's okay. E is contained inside is parameterized by a map of our D, and this map is 1 minus epsilon holder. Oh, I didn't tell you the best part of the theorem. Damn it. Okay. Sorry, guys. Okay. hold on, give me a moment. This is not optimal, right? I didn't tell you anything. I told you that maybe I can find the curve of finite length, but who knows what the length is. No, that Peter-Jones theorem is way better. It tells you that the length is comparable to this quantity. Where comparable, I mean bounded above and below by a constant. This constant is terrible. In fact, people have tried to implement this algorithm, and it's not great. But for an analyst, it's great. So, sorry, that was like the main part of the theorem. All right, let's go back to 1960. Okay, so this is great. So this tells you that something flat is kind of smooth. And the flatter it is, the smoother it is. So what does it mean to be Reifenberg flat? The definition is like somewhat technical. So I'm gonna like just wave my hands a little bit. So just say that if you're set E in the plane, at every point and location, at every point and scale, so take a ball sent at your set, there is a plane. And this plane is close to your set. So if you were a smooth object, you will take tangents, right? But you're not smooth. So you just have this collection of planes or whatever. And if you are more of a topologist, you might want to think about this Reifenberg condition as a quantitative orientability. You have this system of planes, and you have a very strict control on how, like, of the angles between these planes. So something that you should, like, an idea of what you should think about. So this is the Foncke snowflake, of course, and this is the epsilon. So this is parameterized by Hölder curve, and how good the Hölder curves depend by how big your spikes are. How do you get? This is never Lipschitz, this is never C1. How do you get it? Well, if this is 0, that's also called a line segment, which is C1 indeed. All right, so I think I'm running a little late, but it's okay. So there is a theorem here, and this theorem is, I'm lying and hiding so many things, but it's okay. So this is David and Toro. I think 2000, so Guy David and Tatiana Toro for 2012 in the case alpha equals 0, and myself, I don't know, 18, for the case alpha in 0, 1. And what does the theorem says? Well, we know that if beta is controlled, then you're Lipschitz. And if you are Reifenberg flat, then you're Hölder. Can we say something more? Well, if you take E to be some epsilon d Reifenberg flat, where epsilon is small enough depending on other parameters of the problem, which I will not say, plus something else which should look to you now very familiar. I will tell you in a moment. If this is finite, uniformly bounded, in fact, and our k is just 10 to the minus k or 2 to the minus k if you prefer, or just take something that goes small, then E is contained inside, is parameterized by a map. And how is this map? Well, if it was like that, it would be Lipschitz, alpha equals 0, that's David and Toro. But if you require it to be like even smaller, you can get this map to be in C1 alpha. Okay? And so now I'll take 2 minutes to tell you about what I would like to do in the future. And so there is this theorem, right? So what is great about, oh, and the norms depend on this constant in a very terrible way, which is great for analysts still. What I would like to do, right? Well, I think that the one reason that this theorem is great is that this is a characterization. This is an if and only if. This is not. This is just a one-direction thing. So I think the most natural question that one might ask is like, what about the other way? Well, I don't think the other way is correct. I think I have a counterexample for which this doesn't hold, but that's not. So, I mean, the question is, can I, or maybe you, but I hope it's me, can I prove a C1 alpha version of the annually traveling Salesman theorem? Like, can I find the characterization of subset of C1 alpha curve? There is some old work from Campanato in the 60s, in fact, and some other reason that I believe the condition should still, and I like beta numbers, should look still like something, should look like of this type. Campanato is some characterization of function spaces. So he has function, he has a fixed orientation, I have sets. And maybe C1 alpha is kind of an arbitrary choice. It's like my favorite is a function space. Then, so about Hölder space, I don't think it works. I think there is some other work. Or maybe you are like, you really like very complicated function space. I don't know, like you want like base of P, Q, K, R, I don't know. All the like, can we find the characterization of subset of curve of some regularity, whichever your favorite regularity is? That's it.